Okay, great. Thank you for coming back. And of course, welcome me back in person. The trip to France is very interesting. It's been really rewarding because after the pandemic, it's the first real trip to see people. And also the conference, we've been doing the virtual conference for how many years? 2 or 3 years. And you know it doesn't really work. Just like you take lectures virtually is very different than you actually see the people in person. Okay, so I guess during the time that I was in France, we have sort of the half lecture and also the half in-person discussion by Kent. So if you have any question, since I'm back here, just don't hesitate to ask. We can spend more time discussing the materials. You can send me email to find a time to talk. Just let me know. Now, what I want to do today is to talk about a new chapter, Chapter 5. So what is this all about? We have been talking about single random variables, discrete or continuous. And so now is the time to look at things together. And I would say that this is really the sort of another core spirit of this class. One random variable, it is useful if you think about the modeling perspective. I have data sets, I build a histogram, the Titanic data set I Ken went through with you guys. I look at the distribution, I look at the shape, I can draw some statistics, I can say something. That would be useful, but it would be also useful when you start to look at the relationship between two random variables. Now I can give you an example in image processing. You look at an image. You have millions of pixels. Each pixel, you can treat them as an individual random variable, and you look at two adjacent pixels in a space. And they should follow some kind of correlation, because if I am a bright pixel, then the pixel next to me is likely to be also a bright pixel, right? So you have certain kinds of short-range or long-range correlation that is driving the relationship between pixels, right? Same thing will apply for audio speech. Same thing, if you want to do natural language processing, you have a sentence, there will be correlation, right? So let's say you look at TH, that is likely the last word would be E there, right? The word there. So there's correlations everywhere. The moment we talk about the correlation between two random variables, we need to talk about random variable X and random variable Y. So if X has a PDF, Y has a PDF, what do we talk about the joint PDF? What is that thing, the joint PDF? So in this lecture, 5.1, we want to study this joint PDF and joint CDF. Then the next lecture, we'll talk about joint expectation. What is joint expectation? The random variable X times the random variable Y, what is the expected value? You want to talk about the correlation. What do we mean by correlation between two random variables? How do we define independence of two random variables, right? So things will progress from that way. Then you can talk about an array of n random variables. You look at the histogram, you have many samples, you look at an array of random variables. Then you can look at the limit of random variables. Then you become a continuous random process, right? So you can see the progression. One variable to two variables to n variables, eventually to a continuous function. So that would be the progression of this course, covering from the very beginning to the very end of everything you need to know about the random variable. Okay, so let's talk about the joint distribution, or joint PDF, joint PMF, joint CDF, and things like that. So here is a very simple mind diagram that tells you the roadmap of where we are heading to. We were talking about a single random variable with a single PDF. So that's fx. Now we're going to look at this. We have two random variables, x and y. They can be both Gaussian, or one is Gaussian, one is binomial, something. Two random variables. And then we want to look at their PDF. Now, because you have two random variables, then the PDF has to be two-dimensional. Right? You will have one dimension specifying the state of the first variable x1, and then another axis staying the state of the other variable x2. So you have x1 and x2. If you have three random variables, you have x1, 2, and 3. And so you have three states. You have n random variables, then you have n states. You need to look at them at the same time. Okay? So in general, when you look at a high-dimensional probability density function, we're going to use this notation. On computer, of course, you can bold the alphabet by saying that, okay, that is a vector x, and so you have an array of numbers x1 to xn. On paper and pencil, usually I just say big X with an underline to specify that it is a vector, and then there is a small x to specify it is another vector. So that's just a notation. Okay? As we progress to high-dimensional variables, we will use this notation. So why do we study this joint distribution? Well, because joint distribution is just everywhere. If you want to look at image processing, you want to look at the distribution of an image. Okay? So what do I mean? You look at the dog image, you want to classify the dog and the cat. Then the dog image, you will have a certain number of pixels. You have an array. Then each variable will represent a random variable. They have some correlation, they have some distribution. You want to look at that. Usually, this image will live in some kind of abstract, high-dimensional, we call it manifold, in just some weird space. Okay? And then similar images, they will live closer. Different images, they will live at different locations. And then you can start to measure the distance, you can do the clustering and things like that. So the reason we want to study this joint distribution is that there are many practical problems that I can introduce to you once we understand this joint distribution. So what we want to do today is to talk about a few things: joint PMF, PDF, CDF, marginal PDF, PMF, and also independence. I want to cover these. So that will correspond to one section in this chapter. All right, so let's talk about PMF first. That's the easier case. Let's look at this diagram. Now, think about what have we studied? Well, we studied PMF, right, which is a histogram. Is a line, right? So this is a line. So that's the state axis. And then you start to draw all these delta functions, right? So this is Px with a capital X here. So these are the PMF of a random variable. You draw it on a one-dimensional line, and then you have the height. So when you have a pair of random variables, x and y, what you will want to do is the following. Instead of having just one axis, you will have another axis, x and y. You will have a pair of axes, x and y. And so now you will not just have the delta functions along the x-axis, you will also have a delta function along the y-axis. So you have something like this. Right? So you have rows of delta functions. Just like this diagram here, you have the pulses, the blue and the red, and so on. So what is the meaning of each delta in this two-dimensional space? So if each delta, if in the PMF case, in the one-dimensional case, that specifies the probability of having that state, then each delta in this two-dimensional space will tell you the probability of getting a pair of states. So let's look at this diagram. In this diagram, I have a set A, and then I have 5 points. I look at this red dot in the middle. And this red dot has a coordinate of x and y. This is the state of x. Well, if you like the number, that could be 1.25. This number is 5.36. Just two numbers, right? So they're the two coordinates. The point here will tell you the probability of getting this pair of states. A pair of states. That's somewhat different than just getting one state. What is the probability of getting one state? Well, that we don't know yet from this diagram. I need to introduce a thing called a marginalization to tell you the probability of getting an x for all y's. Okay? But here, this red dot will represent the probability of getting one particular x and one particular y. And so the way to read this is that you have this joint PMF. It can be written as the probability of x equals to small x, the state x, and y equals to the state of y. X equals to x and y equals to y. Now, of course, at this moment, you're already thinking, can I just factorize them into probability of px times the probability of py, which means that does it equal to p of x equals to x and p of y equals to small y? Does it equal? They will become equal when they're independent. That's just the beginning of our course, right? Independence means that the two events can be written as the product of the two probabilities. Okay, so this will hold only when x and y are independent. Now, if they are not independent, then that doesn't hold in general. Okay, so when you look at this definition here, this is the definition, and this is sort of the remark. We'll come back to this point later. The definition is just that this is a joint event of x equals to small x and y equals to small y. And they're not necessarily the product of these two. They will become the product only when they are independent. We will give you examples. So that's the joint PMF, and here is an example. You flip a coin, and then you denote it as x, and then you throw a die, you denote it as y. So how many states are there for this pair of random variables, x and y? You flip a coin, and you throw a die. 2 times 6, that is 12. So that altogether 12 states. Okay, 12 states. So I can draw them on this table. You have x equals to 0 at 1, y equals to 1, 2, 3, 4, 5, 6. So you have altogether these 12 states. Now, I can ask, what is the probability? What is the probability of x equals to 3, x equals to 1, and y equals to 3? What is that? That's easy. You go to this table, right? You go to this table. This table has x equals to 1 and y equals to 3. This is the number, so you get 1 over 12. Then you ask, okay, how do you construct this table? Well, I'm just telling you this is uniform. Okay, uniform cross all the possible states. Then you have 12 states, just 1 divided by 12. So this is how I construct the table. But the point is not about how do we construct this table, because usually I will tell you the table. The issue is how to come up with this the joint PMF. I ask you, what is the probability of x equals to 1, y equals to 3? You need to go to this table, find out the coordinate of 1 and 3, give you me a number of 1 over 12. Okay, so that is a simple case. Now, let's work on a harder case. So in the previous example, define the event a equals to the sum of these two random variables equals to 3. And then the minimum of x and y is 1. Find the probability of A and the probability of B. Let me cover this up. No, let's go back to here. So the event A is x plus y equals to 3. And I want to find this probability of getting this event. The table is given to you. Numbers are here. What is the probability? Or in other words, what are the elements in this event? Let's look at it. How can I get x plus y equals to 3? Now, if x is 0, what y will give me 3? It will be x equals to 0, y equals to 3, so that would be this case. Okay? And then now my x can be 1, so my y has to be 2, correct? So what is the probability of getting this event A? 1/6. Okay, exactly like this. The probability of A, I can write it as the sum of these probability masses. Okay, just like the same case when we were studying the 1D case. And then you are integrating, and then you are summing over the event A, so you are summing over all the coordinates inside this event A, which correspond to the coordinate of 0, 3, and the coordinate of 1, 2. And then you look at the table, you ask what are the values, 112, 112, you get 2/12. How about the event of B? Event of B is that the minimum of x and y equals to 1. Okay, so if x is 0, and then y is whatever number, then the minimum will be 0. The minimum will be 0. And if x is 1, y is 1, so that will work. That will be 1. If x is 1, and then y is 2, the minimum is 1, so that will work. X is 1, y is 3, that will also work. In fact, everyone works. So the probability will be 6/12. So here it will be the equation, right? So you just write down all the coordinates where this event is true, then you get 6 of them, so 6 divided by 12. The concept of the joint PDF, which is the case for the continuous random variable, is more or less the same thing if you understand how we work for the discrete case. So instead of summing over the pulses, here we integrate the PDF over the area that we're interested in. When you look at this integration, it is a two-dimensional integration, and things will become not as friendly very quickly because one-dimensional integral is already not fun. You need to integrate by parts and integrate by substitution. Now, if you have double integrals, life can just explode immediately. I think this is taught in Calculus B and C. And I really hated that class because it's just so tedious. How do you integrate this two-dimensional thing? And then you need to integrate with respect to x first, and then you need to integrate with respect to y, and then somehow you just mess up the integral and then explode, okay? So, so just be prepared. That will show up sometime. Now, let's go back to the concept. The concept is not that hard. Just think about how do you do the probability for the continuous case. You have a continuous PDF. This is the density function, and I keep mentioning that the density function, the height in the density function is not a probability. You need to integrate. You need to integrate the density function over a period. Then you can tell me the probability, and therefore the height of the density function can be bigger than 1 because the interval can be smaller than 1. Okay, so same thing will apply to here. You have the probability that x is between a and b. That is going to be the integration of fx dx from a to b, right? So now if I have a two-dimensional distribution, then I will need to tell you that the area under the curve, right? So this is the event A. It has to be integration of f. Now it has to be x and y, then dx and dy. Then where should you integrate? It's no longer just from A to B. It has to be over the entire set A. And the set can be an arbitrary shape depending on how you define it. If it is a square, then you can specify the beginning and the end point with A to B and C to D, so you can specify that. If it's not a square, then you need to worry about all these. So here is an example. So consider uniform PDF with this PDF fx on this square 0, 2 by 0, 2. So you have space 0 and 2, 0 and 2. So this is your the sample space. And now, okay, you also know that the height of this PDF is 1/4. Why is it 1/4? It's a uniform distribution because I want to make sure that the integration of this fxy, dx, and dy over the entire sample space, which is from 0 to 2, and the integrate from 0 to 2, has to be 1. The same principle, right? If you integrate over the entire sample space, it has to be 1. And now what is this? This thing is uniform, right? So it's just a constant. It's just a constant. I call it C. So you have this C times this integration from 0 to 2, 0 to 2, dx and dy has to be 1. Then what is this integral? That integral is just 4, right? You're integrating the square. So that will give you 4. And so that means C equals to 1/4. So you know that this is true. And then I will specify the region, call it the event A. So that will be from A to B, right? So this is the x-axis. The y-axis is from C to D. So that is the y-axis range. And I ask, what is the probability of having that event, which is the area of this little square here? What is it? Well, without doing all this calculation, we know that the width is B minus A, the height here is D minus C, and so the area under the curve will be the height times the width, not done yet, divide by 4. Okay? So by just looking at this diagram, I think we can figure out the probability of this event A. Now, if we want to do it more carefully, we want to write down the equation, that will just be the probability of event A, which is the probability of x between A and B and y, right? Y between C and D. And this is an AND event, right? This is an AND event. And so you can write down this probability as the integral, the double integral from A to B for x and C to D for y. And you put in the definition of your joint distribution, which is 1/4, like a constant. Then do this integration, you will get into this number. So that's an easier integration. And now let's do a hard integration. Okay. So let's do this. I'm not sure if I can really do it. Okay, so this is a hard one. So you have an event B. This is from 0 to 2. Okay. So this is the sample space. And I want to specify the event B. B is x plus y less than or equals to 2. Where is this set? Okay. On this figure, where is this set? Triangle? Okay. This triangle, that triangle, this triangle, that triangle. Which one? Okay, so let's do it. Okay, so let's do it slowly, because everyone messes up in every semester. Okay, so let's just do it slowly. Okay, so the first thing, if you forget about the calculus B and C, follow me. You have, you have this equation, x plus y, less than or equals to 2. Ignore the less than equals to, okay? Just make it equals to. what is this line? Okay, so this line is equivalent to y equals to minus x plus 2. All right, minus x plus 2. So where is the slope? Okay, the slope is minus 1. Minus 1. So without worrying about this intersection, right, it has to be this here, right? So that would be the negative slope. And then you ask, is it here, 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 there, right? So then you ask, if my x is 0, substitution, right? If my x is 0, where is my y-intercept? So put x to be 0, then y equals to 2. Then you know that this line would be here. See that? Okay, so that would be the line. Without worrying about, okay, there's an inequality. Okay, forget about it. Just where's the line? Is it the positive slope line or the negative slope line? Where is it? Find out that line. Okay, so once you have found that line, then you need to color the area. Is it the upper half or is it the lower half? Why? No, not because it is less than equals to. Okay, there should be a principled way of telling you whether this is the upper half or the lower half. Okay, here's my trick, the trick I used, and it works every time, is that you ask whether the 0, 0 is included in your set. So here's what I do. So the coordinate 0, 0, does it belong to the set B? This is how I do it. It's very principled. So you put a 0, 0 into the set. 0 plus 0, is it less than or equal to 2? Yes. So that means this point is included. And of course, it cannot be on the upper half. Then it got to be the lower half. Very easy check. Just check. Okay. Now, this line, is it this quadrant or is it the entire half plane? Just this line. Just this line. Just this line is actually the entire half plane. However, we will stop at this x-axis and y-axis because my sample space is constrained to this square of 0, 2, 0, 2. And in some examples later on in this course, you will see that it could be unbounded below. Right? So just be aware of that. All right, so this is the area under the curve you want to integrate. This is the curve. How do you find the area under the curve for this thing? Now, of course, if you're high school, you say triangle, height times width divided by 2, right? You can do it. Okay, but then we want to do it more principled. I want to show you a systematic way of doing this. So how do we integrate? Well, you want to have this fx and y and dx and dy. And of course, that would be a double integration. The reason 90% of the students mess up in every semester is that they mess up of putting these 4 numbers. What are these 4 numbers for this problem? All right, calculus B and C time. Okay, so let's see it. You have this shape to integrate. Okay, you have this shape to integrate. Give me a choice. Do you want to go with x first, or do you want to go with y first? X first, okay, and then I'm going to show you how to do y first. If you want to go with x first, where do you start? 0, okay, so let's start with 0. Where do you stop? Stop at 2? If you stop at 2, then you're done. No. Okay, you're dead. Yes? Okay, 2 minus y. The reason is let's say you start from here. This is 0, right? This is x equals to 0. You go all the way until you hit this point. Until you hit this point. This point. What is this point? This point is 2 minus y. Okay? Now, if you're here, you go to here, then you stop at this point. This is also 2 minus y. Of course, this y is a different y than the other y. Just be aware. Okay, so you do this. You go from 0 to 2 minus y. Then you have an outer integral, that is dy. Where should the lower limit be? 0. Okay, so you have already scanned through all. Okay, so now think about this. The inner integral is just a line. It's a horizontal. It's just one line, one horizontal line in this figure, going from this point to that point. Just one line. It works for whatever y I have. And then you need the outer integral to list out all the possible lines. Okay, that has to include all the possible lines. That has to enumerate all the possible y's. So what would be the range of y? It has to be from 0 to this point. From 0, so this is your y equals to 0, all the way to this point, which is y equals to 2. 0 to 2. Okay? Now, if you put the 2 here, instead of 2 minus y, what are you integrating? You're integrating the square. Okay? So that is the tricky thing. You need to make sure that these four numbers are all correct. Now, of course, I know some of you here in this room are thinking, what should I do if I start with y first? Okay, let's see. What should I do if I start with y first? So fx and y, dy and dx, double integral. Okay, so double integral, dy and dx. Now this time, if I want to integrate dy first, that means I want to start with this point and then go all the way to this. So the lower limit has to be 0. The upper limit will be, yes, 2 minus x. Okay, it all comes from this equation, x plus y equals to 2. So now you have completed one single line, and then you want to exhaustively search through all the entire x range. Then the x range has to go from 0 to 2. So if you don't believe me, you can show by plugging in your fx here, and then these two has to be identical. Assuming that you do it right. If you do it wrong, of course, that's a different story. Okay, so the rest is just calculus. That means I can skip. That's the privilege of being a professor. Oh, yes, question? That will tell you the probability of this event B. The probability of B is this. Okay, so you guys can carry out the integration by yourself. So can I skip it? Okay, so you can do it. So this figure just tells you how do I do this integration. So there are two directions to go. All right, so let's work on an even more complicated example. So in this case, you have a PDF, fxy, and it's given by this ugly formula. And there's a range of y less than equals to x, less than equals to infinity. Okay, so how do we solve this problem? Okay, so let's find the constant c. Okay, so we want to find a constant c. That means we want to integrate this fxy, dx and dy, and that has to equal to to 1. Right? So that's the principle. And then I have a double integral. I have a double integral here. I need to figure out the upper and the lower limit. And now for this problem, how is it? What is the shape of this distribution? Well, we need to draw a two-dimensional diagram, right? So this is x, this is y. You don't need to worry about the exact thing here. This is just a definition of your x, y. We need to worry about the range. The range. So the range says that your x will go from 0 to infinity, your y will go from 0 to infinity. However, your y is less than x. Now, if it is from 0 to infinity for x and y, then of course it will just be the entire quadrant, right? So it will be positive quadrant. But then you have a range, y less than equals to x. What is it? What is it? Y less than x. Yes, please. Is it going to be triangle, a diamond, a circle? Triangle? Yes. Y equals to x line, and then is it upper half or lower half? Lower half? Okay, so let's find out if it is true. So first of all, you look at this condition here. Y less than or equals to x. Ignore the upper and lower bounds, right? 0 and infinity, just this one. Y less than equals to x. Same principle, ignore the inequality, just make it equality. Y equals to x. Where is this line? That's easy. Slope 1, boom. This is y equals to x. Okay. Then you want to see, is it going to be the upper half or is it going to be the lower half? Now this problem is a little bit trickier because you have this 0 is just touching the line, so we can't use this point. But we can use another point. Give me a point you like. 1, 0. Okay, easy. Okay. So how about 1, 0? Is it inside the set? Let me just call it set A. Okay, so A equals to the set. Is it in A? Well, put x equals to 1, y equals to 0. Is y less than x? True. 1, 0 is here, is true. So it would be the lower half. Okay, so that should be the area under the curve. Now, once we understand this, let's fill in the blank. To do this double integration, I have 4 numbers to put in this integral. What should be the lower limit? Going 0 to y. If it is going from 0 to y, it will be here. Okay. Okay, so if you think about from 0 to y, it will be from this point all the way to this point. So that's not what we want looking for. From something else, it will be from something else. It's not starting from 0. Yes? It's going from y. You start from this point, go all the way to infinity. So you start with y, go into infinity. And then dy, of course, it will be from 0 to infinity because you need to cover all the possible horizontal lines. So that will from 0 to infinity. Now, one thing to remind you is that if you integrate with respect to x, your limit cannot have an x. Just simple rule of thumb. If you're integrating with respect to y, your limit cannot have a y. Okay, so here it is okay because you integrate using dx and then you have a y in your limit. That's allowed because your y will work with, the inner integral y will work with the outer integration dy. Okay, so then what? Well, then let's just carry out the integration. It will just be double integration 0 to infinity, y to infinity, c times e minus x, e minus y, dx and dy. Okay, so time to skip all these. I'm lazy. Okay, so you can do this integration, and then ultimately you can show that dot 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 equals to c over 2. And so that means c equals to 2. So that would be the answer. To just as an example, we can also think about if you want to do integration dy first, what should be it? Okay. So if you want to do dy, make sure, I just want to make sure that you know, okay, how to do it. So this is the line, this is the area. If you want to go dy first, integration dy and dx, what should be the lower limit? Okay, it will be from 0 all the way to this point. This is x, okay, it's not y, because you're integrating dy. And then you want to overcome all the possible vertical lines, so that we're from 0 to infinity. Okay. The same principle applies. So this is what you are seeing in the slide. Getting better? All the beautiful memories comes back, right? Okay, wonderful. I still hate it. I still don't like it. But you need to know it a couple times in your life. Okay, so let me talk about marginal PDF. If we know p, x, and y, okay, this is a joint distribution. How do I find px and py? And the way to do it is, if we want to find px, okay, you just integrate over all the possible y's. If you want to find py, just integrate over all the possible x. This statement is difficult to understand, but let me just draw this diagram. You'll be able to see. Okay, here. So this is a two-dimensional thing, right? X and y. The probability of the probability density function or the mass function, the single variable, can be found by integrating over all the possible cases for y if you want to find x. Okay? If you want to find y, you just integrate with respect to x. Here is a very good way to convince you. If you look at this example here, okay, so the coin and the die example, you have the two cases, right? 0 and 1, and the 6 cases, 1 to 6. What is the PDF of x? The PDF of x we know is coin flip. It has to be 1/2 and 1/2, right? We know that. How to get it? Well, just integrate or sum horizontally. This row, you sum all these 6 cases, you get 1/2. You integrate all these 6 cases, you get 1/2. How to get the probability density function for y? Well, just integrate over all the possible cases for x. For each y, you find the x, right? So that will give you 1/6. Okay, so that's the integration. So you can find the marginal fairly easly by integrating over the other guy that you don't care. So px will be the integration over y, summation over y. Fx will be the integration over dy. So that's the marginal. Here's an example. If this is the PDF of fxy, so I have 4 squares, they are all 1/4 each, then the PDF of x will be what? Well, you look at this two-dimensional diagram here. This is your x-axis, right? You see, okay, how many are there? There are 3. So 3 and then 1. It's like a projection. You see from the top. You put your eye here. Okay, you put your eye here. Then this is what you're seeing. Okay, so this is fxy and this is fx. Now I can ask, what is fy? Fy will be here. This is fy. And what would be fy? It will be 1 and then 2 and 1. So that would be my fy. Okay, and if you flip it over, it will be this case. Do you guys follow? So this is just, it's pretty easy if you have this picture in mind. So we put an eye here. This is a more involved example. So this is a Gaussian distribution. So I have a two-dimensional Gaussian. And then it has this joint PDF. I tell you the formula later on, you'll remember this formula. It's actually not too hard to remember. X minus mu x, y minus mu y, each has a square, and then you have 2 pi sigma square in the front. Instead of having a square root, you just take out the square root. Right? So that's okay. Find the PDF of x. Find the PDF of x. Well, find the PDF of x. This is fxy. You integrate with respect to y. Okay, because I want to find fx. And I have fxy, so I integrate using dy. The limits are minus infinity to infinity because this is Gaussian. That's the sample space for the Gaussian. You put this thing inside. You do this one-dimensional integration. You suffer for a couple minutes. You cry and cry and cry, and then you'll get to this formula. Now, why do you say you're just crying? No, it's actually not that hard. Let me show you why. It's not that difficult. So integration, and then you have this 1 over 2 pi sigma square, and then e minus x minus mu x squared divided by 2 sigma square, right? And then we put a square root here. Multiply with another 2 pi sigma square, e minus y minus mu y square divided by 2 sigma square, dy. Okay, so that's just the same thing as this one. Gentlemen and ladies, this one has nothing to do with your dy. You can just pull it out. So you have 1 over root 2 pi sigma square, e minus x minus mu x square divided by 2 sigma square. And then you have this ugly integration of whatever dy, minus infinity to infinity. And what is this? You're just integrating the PDF of Gaussian. That will just be 1. So life is not that bad. You get the result. So this is the marginal PDF of a Gaussian. And let me explain to you why pictorially this is true. So if you have a joint distribution like this, the shape of your Gaussian will just be a circle. It will be a circle. The center will be mu x and mu y. And then now I ask you, what is the marginal distribution fx? Well, you put an I here. Then of course it has to be the bell shape function. If you put an I here, then it will be another bell shape function. Okay, something like this. Now, of course, for a Gaussian, you can have a ellipse like this. And then in this case, you will have a Gaussian like this, and then you have another Gaussian like that. Okay. So for any high-dimensional Gaussian, when you take the marginal, it will still be a Gaussian. So that's the beauty of Gaussian distribution. All right, so lastly, independence. If you have two random variables, they are independent, then the joint PDF can be factorized. Joint PMF can be factorized, just as what we have seen before. So if you look at this example, you have the joint PDF, a joint Gaussian. Since I can write it as the product of two individual Gaussians, that means the two random variables, they are independent. Here is an example that shows you that a PDF with this form is not independent. And here's a reason. If you do the factorization, you have a term that contains only x. You have a term that contains only y. But you have an ugly term that has this cross interaction between x and y. And there's no way that you can separate them. And therefore, you will say that x and y, they are dependent because you cannot factorize. Okay, so one last word, really the last word, is called the independent and identically distributed random variable. So we will come back to this point later. Assuming that you have a sequence of random variables, if they are all independent, in addition, they all follow the same distribution. They're all Gaussian, the same mean, the same variance. then you say that they are IID random variables. Typical examples would be noise. I have a measurement, I take the over time. They are all IID because they are all Gaussian distributed over time. One noise sample for this time instant will have no influence of the next noise sample in time, so they are independent and they're identically distributed. I say that they are IID. Okay? So that term will come back later on, but I just want to mention this terminology so that when you see it, you wouldn't feel surprised. Okay, so I will stop at this point, and then when we come back next week, we'll move on to talk about the expected values. Thank you.